Assalamualaikum warahmatullahi wabarakatuh. My name is Adib Qayyumin Azli from section 5. Today I will present about biodegradable and biocompatible polymers for tissue engineering. So what is tissue engineering? Tissue engineering which aims to repair and replace tissues and organs by applying chemistry, material science, engineering and medicine. Three primary components, namely growth factors such as scaffolds, cells, and biological signaling molecules are divided into tissue engineering techniques. Biodegradable polymers are typically divided into two types, which is synthetic polymers and natural polymers. This is classification of biodegradable polymers. The first one, synthetic polymers. In synthetic polymers, we have aliphatic polyester, polyanhydrides, polyamino acids, polyautoesters, while natural polymers, we have albumin, dextran, gelatin, pectin. Synthetic polymers. The first one is aliphatic polyester. Polyglycolic acid, which is a biodegradable thermoplastic polymer and the simplest linear, aliphatic polyester. It is a durable polymer that shapes fiber. Its use has been restricted due to its hydrolytic instability. Its melting point is 55%, resulting in an insolubility of 225 to 230 degrees Celsius. Application: used in the form of microsphere implants to deliver drugs, steroid, hormones, antibiotic, anti-cancer agents, and so on are examples of drug administered. Next, polylactic acid. Polylactic acid is a thermoplastic aliphatic polyester derived from renewable resources like mixed starch, tapioca product, or sugarcane. It can biodegrade under certain conditions such as the presence of oxygen and is difficult to recycle. Very crystalline, increased melting point, low solubility. And the application of polylactic acid in preparing sutures or orthopedic instruments, PLA, is used. Besides that, polycaprolactam. Polycaprolactam is a biodegradable polyester. It has a medium melting point of around 16 degrees Celsius. And the application is in PCL drugs applications, cyclosporine in the form of nanoparticles, and ciprofloxacin in the form of dental implants are used. Second, polyanhydrides. Extremely reactive and brittle hydrolytically, degrade without the need for catalyst by surface degradation, outstanding biocompatibility, suitable for drug delivery in the short term. Next, polyphosphate. The shift in the side group attached to the macromolecular backbone determines its hydrolytic stability or instability. Used for antigen or enzyme immobilization purpose. Usage under scrutiny for drug distribution. The last one is polyamino acid. Amino acid side chains provide medication attachment points. Due to their resemblance to naturally occurring amino acids, low level systematic toxicity. Investigated as material for suture. Substitute for artificial skin. Natural polymer. We have collagen. The first one is collagen. In mammals, it is most commonly found protein. It's a big part of tissue strand. The application of collagen is used mainly in the delivery mechanism of ocular medication. Second, albumin. It is a significant component of plasma proteins. It is utilized of the processing for particulate matter. The next one is dextran. Branch of polysaccharide composed of numerous molecules of glucose that are bound together in chains of different lengths. For the application of dextran is used in the form of gas for clonic drugs delivery. For gelatin, a mixture of peptides and proteins obtained from boiled bones, connective tissues, organs, and some intestine of animal and produced by partial collagen hydrolysis. Gelatin is hydrolyzed type of collagen that is permanent. For application, gelatin is employed as a coating material, and for drug delivery under oral control, gelatin micropellets are used. Nanofiber scaffold preparation method. To prepare an efficient scaffold for tissue engineering, a number of methods can be used. The high porosity, biodegradable and non-toxic scaffold used in tissue engineering can also improve cell differentiation. Electrospinning techniques, solvent casting, freeze drying, and gas forming are methods used to prepare scaffolds. Synthesis method of nanofibers. The first one is electrospinning. Nanofibers which can be used in tissue engineering as a scaffold. Electrospinning is one of the most prevalent methods for processing nanofibers. The electrospinning technique consists of three components for the manufacture of nanofibers, which is a high voltage source, a capillary needle with a small diameter, and a collector. As we can see, the figure shows the electrospinning. Second, solvent casting. The solvent casting properties for the preparation of scaffold are extremely simple and simple. One method involves dipping the mold into a polymeric solution and giving enough time to extract solution. Adding a polymeric solution to the mold and allowing enough time to evaporate the solvent that forms a polymeric membrane layer is another strategy. Next is freeze drying. To create porous scaffolds, the freeze drying technique was used. Polymers is first dissolved to form the preferred concentration solution in a solvent. The main benefit of this technique is that high temperatures are not necessary. The last one is gas forming. For the construction of highly porous scaffolds, high pressure carbon dioxide gas is used in this process. Gas forming scaffold manufacturing methods does not require organic solvents. This is my reference. Conclusion. To conclude, tissue engineering is aimed at restoring damaged tissues. These structures are formed by biodegradable polymers. So to make scaffolds, various techniques are used such as solvent casting, gas forming, freeze drying, and electrospinning. That's all from me. Thank you.